As we continue working through 11.2, we've already did a good amount of work on geometric series, and I promise you, those are going to continue to come up throughout all of chapter 11. So really get very familiar with the basic form, the convergence terms about absolute value of r, and the a over 1 minus r when you know it converges. Telescoping is not, oh, and by the way, examples 3, 4 in your book are another two good ones to think about with geometric. But now let's talk about telescoping. Example 8 in your book is a good follow-up to what we're going to do. And we're going to do a couple. Telescoping is very interesting. Telescoping goes right along with the definition of series converging. We're going to work on the sequence of partial sums. And unlike geometric series where we have one universal formula for all geometric series, telescoping are unfortunately not that friendly. But as a quick follow-up, telescoping are also not as common either. But still, let's get into it. Let's see what's happening here. So let's look at the series. This is easier done if we actually start looking and seeing what's happening here. So let's look at the series 2 over n squared plus 2n. Now, I have to be completely honest. This is not obvious at all right off the bat. And this is exactly what happens in example 8. But once you have experience, then it gives you something else to consider. And I promise we'll do a second example that doesn't even go quite this crazy. So let's take a look at this one. And let's realize that the denominator could be factored into n over n plus 2. Well, from here, the book would expect you, and this is again, I keep saying it, it's just like the one that they do in example 8. They would expect you to realize that you could use partial fractions to break this one fraction into these two. And if you do the work for that, you would end up getting 1 over n minus 1 over n plus 2. This is the key to telescoping. The idea of telescoping series will be pieces from later terms cancel with pieces from earlier terms. So that's my little hint. That's not a formal definition, but now that we've got this set up, that's hopefully what's connecting it. That we see that subtraction, and subtraction will be the key to things eventually canceling. Now, what cancels here? Well, again, let's write out some terms and see what happens. When n equals 1, I'm not going to put it here. I'm going to use the two separate fractions. When n equals 1, we get 1 minus 1/3. Plus, when n equals 2, I get 1/2 minus 1/4. Plus, I'm using parentheses here to really emphasize both of these pieces are a sub 1. I'm not going to do the arithmetic. A1 is 1 minus 1/3 is 2/3. I would have left it like this if that was my point. But I want to leave this. But for right now, the parentheses aren't doing anything except clearly showing this together is the first term. This together is the second term. N equals 3, 1/3 minus 1/5. Plus n equals 4, 1/4 minus 1/6 plus, and that keeps on going. Now, as I just said a moment ago, these parentheses aren't actually doing anything. So I could drop them. And when I drop them, do you notice what nicely happens? All of this is the third term, but at the beginning of that third term is a positive 1/3, but at the end of this first term is a negative 1/3. These would cancel. Here's a minus 1/4, here's a positive 1/4. These would cancel. Maybe you want to go one further. If you put in n equals 5, you get 1/5 minus 1/7. And that positive 1/5 would cancel with this negative 1/5. That's what I'm talking about up here. And the one in the book, sometimes I think students overreact and they think it's got to be a piece from the second term canceling with the first. No, it doesn't have to be like that. Just somewhere a piece from one term is canceling with a piece from a previous. That is what makes this a telescoping series. And what we are going to do, we're going to work the long, hard way to find the sequence S sub n. We're going to find the general formula for the sequence of partial sums. So I'm going to start simple. All of this was just to get me on track, to realize if I didn't see it right here after I wrote out some terms, it's not like when I wrote out terms here trying to find the R value or anything like that, but I already knew what I was looking for there. That's the other little piece. But in this, I'm establishing that process, that later cancellation with earlier pieces. So let's take a look at our S terms. S1 is A1 is 1 minus a third. S2 is A1 plus A2, so I'd add these together. And still, so far nothing has happened. Until we actually start seeing the cancellation, we definitely haven't gone far enough to find any real patterns. And especially in this first one, because nothing even canceled right off the bat, this first term is really going to be useless to us. But I'll point that out again in a moment. Now, S3, A1 plus A2 plus A3, now we start to see canceling. This plus this plus this, now the 1/3s actually cancel, so I still have the 1 plus the 1/2. This is gone. The minus 1/4 is here, and the minus 1/5 is here. So here's S2, here's S3. Well, 4 pieces here, 4 pieces here, but still nothing too crazy going on. Let's at least go out one more and think about S4. Again, if we're finding patterns, it's not good enough to find a pattern from one term to the next. We have to at least see that it holds to a third term. So at a minimum, I think we all have to get to here. So S4, now adding all 4 of these together, this already canceled. Now this will cancel. So adding all 4 of these will end up with, still have a 1, still have the 1/2. This is gone, this is gone. This is here, this is here. And now, especially if we go back to here and realize, hey, if I just change the order a little bit, if I push that minus 1/3, swap the places of the minus 1/3 and the plus 1/2. Now, hopefully we're seeing some patterns here. And like I said, feel free to include S5. S5 would be 1 plus 1/2 minus 1/6 minus 1/7. And the pattern continues. So what's the pattern? Well, S sub n. Well, S2, S3, S4. They all have a 1. They all have a 1/2. So S sub n all has a 1 plus a 1/2. All those are just given. Nothing changed. So they just literally go right into the general formula. But now, when n is 2, we still have 2 fractions left. Minus 1 over something, minus 1 over something, right? They all have that, but that something is changing. So here when n equals 2, we had a 3. Here when n equals 3, we had a 4. Here when n equals 4, we had a 5. Generically, that is always n plus 1, right? When n was 2, we got a 3. When n was 3, we got a 4. When n was 4, we got a 5. So whatever n was, this is n plus 1. And similar at the end. When n is 2, you get a 4. When n is 3, you get a 5. When n is 4, you get a 6. Now we're always getting n plus 2. We could finally finish this problem, everybody. What we have done through this is, again, the idea of telescoping was that these cancellations would happen. And because these cancellations happen, it gives us a solid chance to get a nice formula for Sn. So we have converted this series problem. I should have noted, right, we're going to do, the whole converge, diverge. If converges to what? Those are going to be our directions for these problems. So I've changed it from a series into a sequence. And now, what happens as I take the limit of that sequence? Well, there's no n. That's here. There's no n. That's here. But now as n goes to infinity, this goes to 0. As n goes to infinity, this goes to 0. So we took the limit of s sub n. We got a nice answer, whether you want to call it 1.5, 3 over 2, whatever. But that is evidence that we converged to that value. Okay, I definitely want to do a second example. Like I said, example 1 in the book, it's only one, it's the second term, something cancels with the first. The third term, something cancels with the second. Here we had to stretch a little further, but that's the idea of telescoping. But here's a quick little warning. There's no shortcut here. What some people like to do is they just write out some terms and they just see things canceling. So they cross off the 1/3. They cross off the 1/4. They realize the 1/5 will cancel. They realize the 1/6 will cancel, and that hey, everything canceled except for 1 and the 1/2. And they say, hey, converges to 1 and 1/2. They got the same answer we did, but that's garbage, everybody. You can't work like that. That's assuming that everything would cancel. And while that may be a very valid assumption because we see it canceling, you need more formal proof work than that. And the second thing, which I'll point out after we finish our second problem, those pieces at the end, these are still here. The reason this added to a nice total is because these little pieces at the end are going away, essentially. That doesn't necessarily have to happen. So, let me show you another one. Let's go to the next problem. Let's look at the series e to the minus n minus e to the minus n plus 1. Okay? Again, it's already two terms, unlike this one that the book expected us to realize that we could separate those fractions. Here, and then we had the subtraction to give us that hint. Here, not quite so obvious. I mean, it's already has that subtraction built in, so we didn't have to do that extra first step. So maybe that gives us a hint that it's telescoping. So I'll try plugging in. I get e to the minus 1 minus e to the 0 plus. That's n equals 1. Oops, I'm sorry. I wanted that to be a minus 1. Minus n minus 1. So that'll be an e to the minus 2. Plus, now when n equals 2, I get e to the minus 2 minus e to the minus 3. And then when n is 3, we get e to the minus 3 minus e to the minus 4. And that continues. And now we're seeing that same cancellation. We're seeing parentheses grouping pieces together just to kind of clearly show all this is the first term, all this is the second term. But those parentheses once again aren't doing anything. We're once again seeing piece from here canceling with an earlier piece, piece from here canceling with an earlier piece. Now it's happening a little quicker. This first part of the second term canceled with the last part of the first term. The first part of the third canceled with the last part of the second. But again, no matter how it cancels, pieces are canceling. That gets me on track for telescoping. We still have to do the Sn work. So I'm going to look at S1 is e to the minus 1 minus e to the minus 2. S2, by the time I've added these, this is already canceled. So I get e to the minus 1 minus e to the minus 3. S3, now that I get to here, these cancel. Again, everybody, I'm doing this a little fast, but certainly if you want to write it out the way I was doing here and then do your cancellation. I was pointing to the cancellation here and writing the result, but you could write it all out. S2 is this plus this, then clean it up and get to here. S3 is this plus this plus this, then drop the parentheses and clean all that up, and you'll get e to the minus 1 minus e to the minus 4. This time I only have 3 terms, but I'm already seeing the pattern. Here I had 4, but I pointed out this just didn't work with the pattern, so really ignore it, start here. And then we had our 3 terms to see some pattern. You could always go more if you need to. Like I said, if you went to S5, 1 plus a half minus a 6 minus a 7th, everything still holds. That pattern still holds. So similarly here, what do we think about Sn? Well, they all have the e to the minus 1. But then here, they all have a minus, they all have an e, but the exponent is changing. And, as we saw, when n is 1, I'm getting a negative 2. When n is 2, I'm getting a negative 3. When n is 3, I'm getting a negative 4. Generically, I'm getting a minus n minus 1. I mean, some people, you're looking for patterns. Again, don't go crazy with this, but some people will notice that here, that n plus 2, well, the n plus 2 is also a part of the fraction here, but the n plus 1 was not. So we can't just bank on that and just say, well, that's exactly what's going to happen. But there are some similarities that come up. Some people might struggle a little bit to find that pattern. You see what's happening, you know it, but how do you just get that general formula? So sometimes just going back to the beginning can help a little bit with that. Maybe it's not so perfect like we saw here, but it can kind of at least give you a little guidance. But now, what happens? As n goes off to infinity, the e to the minus 1, or 1 over e, I mean, all right off the bat, that's a funny little secret. I could have rewritten these as fractions. 1 over e, factor out a negative, and this becomes 1 over e to the n plus 1. So, there's a little bit of fractions I could have worked with here, but I wanted us to see a slightly different form than the fractions that we saw up here. But that piece is still just there. Here, n goes to infinity. E to the minus infinity minus 1, that's becoming an e to the minus infinity, which we know is 0. So this also converges, and again, to 1 over e to e to the negative 1. But once again, we have another convergent telescoping series. One quick thing. So, again, as I pointed out up here, and the same thing happened here. People say, well, why can't everything crosses off? And the answer was e to the minus 1. Why did I have to bother with all this work with Sn? Well, just realize one little thing, everybody. If that was a positive n instead of a negative n, this would have been e to the positive infinity, which is infinity. So you would have had e to the negative 1 minus infinity is negative infinity. And now all of a sudden this series diverges because this sequence has a limit of an infinity. So that's why I mean, everybody, it's so easy to just cross off and just think everything's working perfectly, but you gotta understand what's happening at the end here. And once again, just like here, we got lucky that these last pieces went to 0. That's why we got nice answers for both of these. But if that last piece went to infinity, for example, well, then the whole series would diverge. Okay, a little bit more to finish up this section. We are very close, but we have a few more important pieces to be discussed. Next is its own special series. Not a type of series, literally just one series. And it is known as the harmonic series. It is the series 1 over n. One quick thing, I definitely could have noted this in part 1. Just when you make your summations, this is a little nitpicky point. Some people end up drawing these like they're cursive E's. That is a completely different notation. So again, try. I know every once in a while I do it quickly and it gets a little messy, but these are very hard, sharp lines when you make a summation symbol. And it's almost better, instead of trying to do it all in one like a cursive letter and making it look like an E, it's almost a better habit to draw these separate line segments to really show that straight line that shows the sigma for the summation symbol. But that's just a little aside, nothing too big to worry about. But back to this. This is the harmonic series. If we actually started filling in terms, right, we just keep getting 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and we just continue. It's like we're getting 1 over every fraction, right? By getting 1 over every whole number denominator. It's, why is it called the harmonic series? There's some other connections to other aspects, but that just gets its own formal name. And like I said, it's not like it's so incredibly interesting, but it comes up often enough that we just want to have this result. The harmonic series diverges. And that's just a fact we're going to be given. The book gives a kind of tough little proof to try and demonstrate that, but again, that's just a fact we're going to need. It's a very interesting historical fact because when people first started looking at series, this is one that for the longest time mathematicians thought actually converged. And it had to do with their poor computing power. I forget the exact value, but it's like if you take this out to something like the 1,000th term, you get 21. And if you go out to the 10,000th term, it still looks like you're hovering right around the value 21. So you think about the era, I mean, I'm not just talking about a decade or two ago, I'm talking about centuries earlier. We had no computer technology. So getting to the first 1,000 terms was a lot of work. So when they got out to the first 1,000 terms and then pushed it so much further and still felt like they were getting the same sum, they thought it converged. But it took a lot of proof work to show it diverged, and that it's something like if you go out to the millionth term and add them all up, now you get to 22. But it's like you got to go so far to get to that next piece. These fractions are so little as you keep going, but eventually they add something of weight. So like I said, everybody, it's strange. As we keep going deeper and deeper, there's a lot of instinct people have, and you got to be careful you're not developing wrong instinct. So for instance, just going back here for a moment, I pointed out the keys to both of these series converging were these end pieces all going to 0. But there's more to it than that. It's because we did all this other work that was enough that gets us to that it converges. But that's just because the terms themselves are small, that's not enough to guarantee that things are going to add up nicely. And that leads us right to our next result. We have a theorem that tells us if this series converges, then it is an absolute guarantee. If the series converges, it is an absolute guarantee that the underlying sequence has to go to 0. But realize, logic, it's not enough to do this in reverse. We can't say, if the terms themselves go to 0, then the series will converge. That's not how it works. That would be the converse of this statement, and it's not true, and this is an example of that. If you just looked at the limit of 1 over n as n goes to infinity, that's 0, but the series itself actually diverges. So why do we bring this up? It's not the converse that's helpful, it's the contrapositive. Negate the conclusion, and then you do get to negate the assumption. That is logic that works, and that is helpful for us. The contrapositive would say, if the limit of a sub n does not go to 0, then we automatically know the series with a sub n as the underlying sequence, then we would know that does not converge, so therefore diverges. That's the statement that's going to be helpful. And this is formally called the test for divergence. But again, I can't say it strongly enough. All you get out of this is if this doesn't equal 0, then the series diverges. If this limit does equal 0, you know nothing. Maybe the series diverges, maybe it converges, but this test isn't cutting it. So let's try a couple of these. Let's again converge or diverge. Let's look at the series 4n squared minus n plus 1 over n squared plus 3n. Well, how would you know what to do? Well, in reality, everybody, we basically have 3 tools at our disposal so far. Is this geometric? No, it is not. You can write out some terms if you like, but the n is not in the exponent. It definitely doesn't fit the AR to the n form that we saw in one of our examples, but even in our other examples, you could write out the terms, you could look at the general form. There's nothing about this that's geometric at all. There is no common multiplier, so it's not geometric. That's not going to help. It doesn't have the two separate fractions, or at least the two separate pieces, to even have the possibility for telescoping. So kind of by default, this is our last tool. But that's a big part as you go through the homework in 11.2. Always consider those three options. It's gonna be one of those three. So some of us, maybe now that we've got a little more practice, or now that I've kind of pointed you towards it, maybe you're already focused on that, and you realize that if this is your a sub n, that limit is 4. And again, everybody, I give you full permission to do the same things I am using. S sub n is always considered the sequence of partial sum. Instead of writing all this out again, I mean, maybe you want to write it all out. Maybe you do want to do the limit of this. Make sure you set up limit notation, everybody. Some people just keep writing summations, then all of a sudden they're getting equals 4. That's not true at all. The limit of this, just this, equals 4, but that has nothing to do with the summation, at least not right now. So you can abbreviate like I did right here, and you can get some quick work, and that still shows me you know what you're doing. If you want to write out a little more, again, the limit of all of this, then you focus on your dominant terms, then you cancel down, and then get to here. But now we all get to make the same result. That limit does not equal 0. Therefore, this series diverges, and we are using the test for divergence. Diverges, some people just call it the divergence test, the test for divergence, either way, and that's what I'm talking about. Earlier, you didn't need to put any converges by or diverges by. You have R. R is always the letter we use for geometric, so that's clear to me. You don't have to say by geometric series. You just make your case based on the absolute value of R and whether it's less than 1 or greater than or equal to 1. Telescoping, well, you found the whole formula for Sn. You found the actual sequence of partial sums. So again, there's no extra explanation left at the end. But here, technically you're using a new test. We're not looking at Sn in this problem at all. We are entirely basing it off of this test, so that should be a part of your conclusion. Okay, so there's one. Number 2. Here's one. You could actually play a game with Sn here and actually get that this diverges, but you could also do the test for divergence. This time, the limit just simply does not exist. See here, I wrote it out. Same thing, you could write an here again. Again, an is always, whatever problem you're working on will always assume that is just the underlying sequence to go with that given series. But here I wrote the whole thing out, and this just keeps bouncing. +1, -1, +1, -1, +1, -1. The limit does not exist. So again, does not exist, still doesn't equal 0. So we still get to make that same conclusion. And one more like this, number 3. Let's take a look. Remember this? We just pointed it out in the last video, and we did it for something just like this. That needs to stand out. The limit of that, again, it's not just that expression. The limit of that expression, whether you write it in this form or you clean it up a little bit, but it's the same thing, that limit is the definition of E. E is still not 0, so we once again get diverges by the test for divergence. Now you may say for a moment, well, wait a second, what about the ones that converge? But realize what I just said. You're never going to use test for divergence and come up with a conclusion that a series converges. And again, go right back up here. If I said, what about this one? You say, oh, the limit of this equals 0, but that does not allow you to go backwards and say the series converges. And in actuality, this is the harmonic series and it diverges. So later on, we'll have more tools so that if the limit does equal 0, you'll have a better sense of what else to try. The divergence test didn't help, but what else might help? What else can we do? Okay, last piece. Got a lot of good work here, a lot of good problems and discussion. The last thing, the book ends this section with a fairly big little theorem. And let's just quickly talk about what that theorem actually says. So this is Theorem 8 on page 754. This sounds very, very important. And in reality, I'm not trying to underplay it. It is a very important theorem, but it's not going to be as helpful as it first seems. Because what it says, Theorem 8 starts by saying, if we already know that the series A sub n and the series B sub n converge. So we're already starting off with a very big assumption. If you know you have two convergent series, then we get to make these conclusions. Then the series of A sub n plus or minus B sub n would also converge. If you add, and the way you could break it up, that this would be the summation of A sub n plus or minus the summation of B sub n. You're not always able to split these up, right? If we have integrals, the integral of f of x plus or minus the integral of g of x, we could always treat them as two separate integrals. But you could only split up a summation if you already know each piece of that summation already converges. So that's in our book. It's actually parts 2 and 3 they do this. And they also introduce some extra number c. The series c times a sub n would also converge, and it would equal c times the series a sub n. So that this number can be pulled out as a multiplier. Like I said, it seems really helpful, but unfortunately the pain in the butt is that you have to already know that these two already converge. So let me just give you one quick example to at least point out how this could work. Example 11 in the book does exactly this. I'm going to use a different example. Let's take a look at the series. Let's have 5 to the n minus 4 all over 7 to the n. Actually, let's even make those n minus 1s. That'll make this a little easier. If this minus 4 wasn't here, 5 to the n minus 1 over 7 to the n minus 1 could be grouped together as 5 over 7 to the n minus 1, and that would be geometric. So that's kind of the key here. Let's think about what would happen if I tried to separate. I can't say it equals these two separate summations. I have to already know the individual pieces work, but let's take a look at breaking this up into two fractions. Well, if I look at this piece, this, like we just said a moment ago, I can rewrite that as 5/7 to the n minus 1 power. A would be 1, r to the n minus 1. This is a convergent geometric series. Minus, over here, well, let's just play a tiny bit here. Let's kick that 4 out in front. And then I have 1 over 7 to the n minus 1, which I could treat as 1/7 to the n minus 1. Now a is 4, r to the n minus 1. R here is different than r here, but the absolute value of r is still less than 1, so this also converges. So this converges with an extra multiplier, so the whole thing converges. This converges, so subtracting them will still converge, and this will converge. This can be broken into these two separate series because I realize these two separate series both converge. So you could write as a final conclusion, this converges by theorem 8, but this is almost easier just to explain. This is convergent because it's the difference of two convergent series. That's about as much as we'd really have to write for one of these problems. And like I said, it's maybe a couple in the homework will work out like that. Not too many. It's a nice idea, but it completely falls apart if any one of these doesn't work right. Swap these places. 7 to the n minus 1 over 5 to the n minus 1. Now r is 7/5. Now this piece diverges. You don't get to go backwards and say this diverges. That is one of the biggest trouble spots for a lot of students in this section. They are so accustomed to, well, if this doesn't happen, then the other must. But you have to be careful on what your theorems say. This does not say if a piece diverges, subtract that from a piece that diverges, the other piece it's none of that. The only logic here is that if both of these converge, then this also converged, and that's what we had here. Just like we saw with the test for divergence. You could only conclude that it diverges if this limit does not equal 0, and that's what happened in all three of these. But if that limit does equal 0, that piece is irrelevant. Maybe it converges, maybe it diverges, but that just means we have to try something different. So, I really hope just from these first couple of videos from 11.1, 11.2, you're realizing we're getting some slightly different nuances that we're focusing on. There's still a lot of problems, as far as like how do you do well in math? Well, you go do homework problems and practice. That's certainly still fair game, but to realize the nature of the problems, you have to understand some of the initial theorems, some of the initial tests to make sure you're using them correctly and that you therefore make the appropriate and right conclusions. And again, keep saying it, that's just going to continue. 11.3, 11.4, 11.5, 11.6, all we're getting are just new tests. Some of them are like the test for divergence. We could only make one conclusion based off of them. Others are a little more friendly, kind of like the geometric series. We'll be easily able to see that either yes, it converges or no, it diverges. And we'll be able to conclusively make that from one test. But that's the direction we're going.